Welcome back to the course on architectural design of ICs. So, in the last class we have seen that control 2's complementary circuit, 1's complementary circuit we have seen, then we have seen control 2's complement circuit, that means within 2's complement circuit how we can implement the 1's complement circuit too, and after that we have seen sum of n natural numbers how we can do, okay, and we have drawn the circuit of sum of n natural numbers. That means I can do it in different way, that means I can do it parallelly or I can do it sequentially. So, the parallel implementation of sum of n natural numbers, if the number of sum, that means if I want to add more numbers. So, at that time it becomes, if I just do it in parallel manner. So, at that time I require more of hardware, that means more number of adders. Okay. So, for that reason whenever the n, or if I ask you to draw a circuit for n considering 1024 or 2048 number. So, at that time it requires n minus, as it requires n minus 1 number of adders. So, that means as an n increases, so that much of adder I require. So, more the number of adders I am increasing to the circuit, that means the consumption of the area and power, that also becomes very increases linearly with the number increases as it is n. So, for that reason what we have done? We have done that sequential, that means implementation of that algorithm. So, we have seen that, we have seen the algorithm and then we have developed the corresponding circuit for that. Okay. Let us go back to the corresponding. So, if I just want to add something, that means suppose I just want to draw the previous circuit, and let me tell you one thing. In the last class what we have seen, that in 2's complement circuit there was a silly things which is missed at that time. That is, in the 2's, first I will start with that 2's complement circuit and then we will come to that sum of n natural numbers. So, in 2's complement circuit what we have seen, that suppose if I am having let us consider this thing. So, if I consider this, that means two control signal which is E and C, and I need the functions, that means here whenever this E equals to 0. So, at that time the function, that means the corresponding output will not be changed, it will remain same as the input. So, whenever E is 1 and C is 0, at that time it will give me 2's complement circuit. When E is 1 and C is 1, so at that time I will get 1's complement circuit. Okay. So, I think in the earlier that means class it was mentioned as 0, but it will not mention it is not 0, it is 1. Okay. So, when both E and C are 1, so at that time it will give me 1's complement circuit. The circuit will remain same. Now, I will explain how it works basically. So, the circuit was like C I equals to A I plus C I minus 1, and the A out was A I XOR with E C I. So, this was the logic for designing the 2's complement, control 2's complement circuit. So, if I just implement this logic, if I just drawn the circuit for this particular expression, so at that time how, what I will get? I will get, that means I need for 4-bit if I consider. So, at that time how it will work, how it will look like? So, it will look like this. So, here these things. So, at this particular I need one AND gate for this particular function. So, each of this another input will comes from the AND gate as I am XORed with the corresponding bit position. So, this is A0 and this is the one of the input of this particular AND gate, that is this enable signal, correct. So, where from then I will get this Ci? Ci basically is generated from the this particular equation. So, that means for this, as Ai is not there, that means beforehand of this Ai is not there. So, directly it will come. So, from here I need the OR gate which will come to this, each of these is connected with this OR gate. Okay. So, now one of the input of this is this and another input of this is this. So, here this to this, that means the previous input along with the previous carry. So, here these things and this is the carry. So, this is the C I minus 1, okay. And this is A out 3, this is A out 2, this is A out 1 and this one is A out 0. Now, consider what was my functionality. So, functionality is if E is 0 and C, whatever the value of C is, the function will remain unchanged. That means, it will same as input and output will same. So, if you put, that means if this is the E, okay. So, if E is 0, at that time what is the value of this? Each of these output is 0. That means, so in XOR gate we know that if any of the input is 0, so at that time output is nothing but the other input, right. So, that means here if it is 0, so at that time A 3 will directly come to the A out 3. Why? Because if you see that what is the expression for XOR gate? Expression for XOR gate is A B bar plus A bar B, correct. So, if I put that B equals to 0, so that means now this is A and plus this is 0 means this is 0. So, this is A. So, that means if one of the input is 0 in XOR gate, so the output will be same as the input. So, as each of these bit is 0, when I put the value for E equals to 0, so at that time the function remains, that means the input and output that are same. So, next is that whenever this at the time it is 2's complement, right. So, whenever E equals to 1, so that means this input, that means this bit is 1 and Ci equals to 0. So, at that time what happens? So, 0 means here this bit is 0. So, this will come to 0, okay. So, this is A 0 and then from here if you just see that each of this that means carry generated from this particular position, that is being forwarded and it is added to the corresponding, that means it is ANDed and that means what is the logic behind 2's complement? That means you just add 1 with the 1's complement circuit, right. So, that we are basically doing whenever we are putting this E equals to 1 and C equals to 0, at that time we are just, that means the carry generated from the previous the stage or previous section, that is being forwarded to the left hand side and that is added or XOR with to get the corresponding 2's complement circuit. Okay. And for if I need 1, that means 1's complement circuit. So, at that time what the control value I need, that is 1 and 1. So, that means at that time instead of 0 this will be 1. So, 1's complement circuit means in the previous class we have seen that 1's complement circuit means if instead of 0, if this bit output is 1, so automatically this will be just inverted of the input. That means instead of 0 here, if I just put it 1, so that means what will happen? Now, this will be active. So, at that time XOR gate's output, that will be A bar. Okay. So, here I need 1, okay. Each of these should be 1.
So, E I have set already 1. So, now if C I minus 1 that is equals to 1. So, 1 and 1 this will be 1. So, it will be inverted. So, that one of the OR gate input is if it is 1. So, at that time no matters what is the other input, it will not depend on that. If one of the input is 1, so automatically this will be 1. Okay. So, that means now 1 and 1 it will be giving you 1, this will also give you 1 and this will also give you 1. So, each of these AND gate output if it is 1, if it is 1, so at that time this A out will be just bar of each of the input. Okay. So, that means using this particular circuit now I can implement this 2's complement circuit as well as 1's complement circuit. Okay. So, now next. So, in the next this was the that means functionality, or this was the circuit for 2's complement circuit and along with the 1's complement circuit in the same module, right. So, after that what we have seen? We have seen another example, that is sum of n natural numbers up to n. Okay. So, what I said that for this I require parallel implementation of that requires n minus 1 number of adders, and another implementation technique is that this expression also I can write as n minus n plus 2. So, this also here I require what? I require one incrementer and I require one multiplier block. So, when this n value is large, at that time this will also give you the parallel implementation. That means, it will not depend for so much whatever is the value or whatever is the length of n, it will not wait for that much of clock. Within one clock, if I just want to add or if I just want to get the result of this, at that time I have to implement this kind of architecture or this kind of architecture. If I have, that means at that time what is happening? I need the circuit is related to, that means it is require more. Here I require multiplier and here I require incrementer circuit. So, but if I need, that means if my major concern is that area. So, at that time what I can do? At that time I can implement or I can follow the sequential implementation of that. Okay. So, sequential implementation of that, at that time what I have to do? I have to write the algorithm for that. So, the algorithm we have seen and then corresponding algorithms architecture also we have seen. So, what we have seen in the, that means in the last class, that means I am having 3 registers where I am having S, N and I, these 3 register I was having. Okay. So, and then I require one particular adder circuit, right. So, from where this S and I value is basically added and then it is going back to the corresponding S circuit, and I need one circuit where I need to compare whether that is N and I both are same. If it is same, so at that time what it will do? It will go here and it will stop the corresponding counting. This is nothing but a counter. So, this will stop count or it will just initiate from the starting value again. Okay. And this will come here and it will say that okay, I need, that means I am having one buffer over here, I was needing one external bus and this is the thing. So, this is the corresponding, that means whenever this basically this particular signal also says that basically as this is running in a loop. So, at the time unless and until these two values are same, at that time the computation will be over. Okay. So, that means the loop will break and it will produce the result at the output bit, or I need output bus. So, or I need the output should be, that means the loop has done its job. So, now you just produce the result at the output bus. So, how can I do that? So, this is the terminating condition, that means whenever n and I value they both are same. So, at that time it will come. So, this, that means this is just a single bit, as this is a comparator. So, this will produce one single bit output. So, single bit output will come here and it will activate this buffer, that okay, this now at that time this S will be gone to the external bus. So, this is the external bus. And what I need? I am having this, this is initial value. Okay. So, here I think it will be clear, okay. Here it will be load and here it will be in init. Okay. So, for that reason what I need? Basically the algorithm was something like that means output is S and initially S equals to 0 set to 0, and this is one, that means, or sorry, load the values of n. Then basic the logic for this is, if I equals to sorry 1 to n, then S equals to S plus I. That means I need to add 1 plus 2 plus 3 plus something like up to n, right. So, that is why I will be changed to 1 to n, and at that time S will be, in each case S will be added with the corresponding I, right. That means initially the I equals to 1. So, S value is, initially I said S value equals to 0. So, 1 plus 0. So, that means then again it will come back here 1, then 1 in the next cycle it will be 2. So, 1 plus 2, something like this it will just do it. Okay. And then, so this is the logic for computing 1 plus sum of this particular n natural numbers. So, this particular is very much okay, it will give you or it will produce you the corresponding whatever you desire to design, that means the sum of n natural numbers. So, my point is that here now can I optimize this circuit, or can I, that means from this particular algorithm can I see something, that means I can reduce it more. Okay. So, how can I do that? Here you see this particular n register, okay, that is once it is loaded. So, after that it is not doing anything, it is just sitting idle. That means, once it is loaded, then each of the cycle it is coming here and then it is just comparing the corresponding I value. Why it is sitting idle? That means, in each of the clock cycle I is basically doing its job. That means, this is a counter, that means I is now next 1, then plus, then 2, then 3, then 4, then 5, something like this, it is increasing in each of the clock. Thus, S registers, how it works? In each of the clock it is by basically changing its value from the older value to the newer value, newer sum value. But this n is not doing, only at the, that means starting of this init signal it is loaded from the external bus, what is the value of n, and then it is sitting idle, that value for n, that is not at all changing in each of these clock cycles. So, that means can I reduce or can I remove this n? So, remove, why I need to remove it? Because if this n value is, let us consider, that means 2048. So, 2048 means I need 11 bit for considering this 2048. So, that means I need 11 bit registers over here. So, if I can reduce these registers, that means obviously I can reduce the number of transistors. That means I need 11 D flip flop. So, if each of the D flip flop requires 4 number of NAND gate, So, that means total 44 number of NAND gate I can reduce. Okay. So, in terms of area or in terms of power also I can get the benefit. So, that at that point, looking at that particular point, now my that means intention is that can I optimize this particular circuit keeping the functionality same. So, at that time there will be a small change in this particular section. So, what will be the change? If I just, so what was the logic initially? For I equals to 1 to n, s equals to s plus I. So, instead of doing that, if I just change the logic something like this, for I equals to n to 1, s equals to s plus I. Okay. So, that means, this means what? The here what I need one incremental circuit, which is or up counter circuit, that means it is increased by 1 in each clock cycles. So, here I need decremental circuit. So, the initial value of this, that means I do not need any values or any storage for keeping the value n, what is the value for n. So, here in the counter itself, in the earlier logic what we are doing, we are that means from the external bus we are knowing that okay, users have selected the n value is something like this, then each of the clock cycles we are just basically checking whether that I value, the up counter value, that has been reached to the n. So, whenever it has reached to the n, the computation will be over and the corresponding output will go to the external bus. So, instead of doing that, here in the counter itself, if I load the initial value of n and then we start decrementing it, whenever we will that means here the logic will something like what 3 dot dot dot, my logic initially was something like this, but now my logic has become something like n minus 1 dot 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 plus up to 3 plus 2 plus 1. That means, I have just reversed the order. Okay. The functionality is remaining same, but I have just reversed the order in order to that means reduce the corresponding architecture. So, if I just change this logic from I equals to n to 1 and s equals to s plus 1, s plus I. So, at that time what will be the architecture for this? So, the architecture for this is now what? I need 2 registers now. Okay. This is S and this is I. So, I is now one decremental circuit. So, what I need here, this is the load values. So, that means this will load the value of n and this is the clear signal initially S, that means this is the storage, some storage. So, initially it will be set to 0, okay, and then this will come to the adder circuit, okay, and then again it will come back to these particular things, storage. And here what I missed, this is the external bus. So, what is remain in this particular circuit? How can I set the corresponding, that means the terminating condition of the loop? So, in the previous what was that whenever this I and n both are same, so at that time the competition is over. So, now here what is the terminating condition? That means whenever this corresponding decremental value that means come to this particular 1, sorry, whenever it will reach to 0, that means up to 1 I need to add. So, whenever it will be come to 0, so at that time the whole computation will be over. So, that means the 0 value will not be entertained, or that means as I said that n to 1 it will just count. So, that means now here I need whenever, how can I sense this all the bits are 0 0 0 0. So, for that reason what I need? I need one NOR gate. Okay. So, NOR gate, when all the input bits are like 0, so at that time it will produce 1. That is the logic. Okay. So, that means now this will come to this and this will again come to that. Okay, that means stop the counter, stop counting, and this signal will come here to says that this is a computation over signal, or you just here it will be like enable this buffer, so that the corresponding edge value gone to the external bus. So, that means here that means previous slides, if I just see this architecture. So, at this particular things what I require, area wise what I require, 3 register, 1 adder, 1 comparator, right, and 1 buffer 2. So, in this particular thing, in this particular architecture what I require? I require 2 register if I consider for this S and I, 1 buffer, 1 adder, and instead of comparator what I require? 1 NOR gate. So, that means now I can reduce 1 registers over here, and instead that means in comparison to the comparator, 1 NOR gate also will require lesser number of hardware. Okay. So, that means now I can say that area wise I can save just doing that means a simple trick I can reduce the hardware. So, reducing the hardware, that means obviously that will benefit in terms of power too. Okay. So, this is a basic, or this is a that means very simple things how we can do the optimization whenever we are implementing it from the algorithm to the architecture. Okay. So, thank you for today's class. Again we will see some interesting the circuit implementation techniques in the next few classes. Thank you.